The second part to this question is two particles colliding in one dimension. So we have two particles. Now both of these could be moving in the same direction. They could be moving in opposite directions as well. I've simplified it to start off with. Particle 2 is at rest, particle 1 moves and they collide. Now we don't know what happens after the collision. We know that during the collision each experiences an impulse that's equal and opposite. So the one to the right is experienced by particle 2, one to the left experienced by particle 1. What could happen is both particles could move to the right, or they can move in opposite directions after the collision. And that has to do with the following two factors. One, their masses and their speeds before will dictate what happens afterwards. So that's if both of them experience an impulse, the impulse of one equals the impulse of the other with a minus sign in front, rearrange it and you actually get the principle of conservation of momentum. We can't assume that these spheres are 100% elastic though, so we also need to apply Newton's elastic law to it. Now that formula is a special case of Newton's elastic law when you have one object moving and it strikes a stationary object. The proper Newton's elastic law formula, I suppose, that I'd like to use is that one. And you'll see that the second one, minus E, is equal to V2 minus V1 over U2 minus U1. When one of those particles equals 0 for the velocity before and after, as in the case as in the case of a wall, then it reverts back to the special case, which is minus E is V over U. So I've basically been giving you a simplified version of the formula so far, just to get you used to it. Before I go any further, remember there's two possible extremes for E. E could be equal to 1, E could be equal to 0, but it's definitely somewhere between those. So E is always less than or equal to 1, and E is always greater than or equal to 0. If it's 1, it means that the collision is fully elastic, there's no energy lost. And if it's equal to 0, it's completely inelastic. When the particles collide, both of them will stop. Okay, so let's get on with setting up a question, and we'll work through one of the examples in a textbook. So, smooth sphere A of mass 4 kg moving with a speed of 6 meters per second collides with a smooth sphere B of mass 2 kg moving in the same direction with speeds 3 meters per second. The coefficient of restitution is 0.6. Now, with that information, I always draw a table. It may seem like a bit of too much work for you right now, but believe me, start drawing the tables, and when we deal with two-dimensional collisions, you'll be able to manage the data a lot easier. So just get into a good habit. In terms of the information, they're both moving in the same direction, so I'm going to say that's to the right, in which case they're going to be both positive. So same direction, they're both positive. Obviously opposite directions, one will be plus, one will be minus. I fill the masses in there as well, and I don't know what the velocities or the speeds are after the collision, so I'm just going to call them V1 and V2. Okay, so that's up the top. There's my E value as well. So what we need to do is apply the principle of conservation of momentum, where particle A is the first particle, so it'll be m1u1, so 6 by 4, plus m2u2, that's 3 by 2, equals m1v1, which is 4 by v1, plus m2v2, which is 2 by v2. So you can see it there. We get an equation then which is 4v1 plus 2v2 is equal to 30, so 2v1 plus v2 is equal to 15. The second thing we want to do is apply Newton's law of restitution. So I call it NER, he calls it NELR. Same thing, same difference. So minus E is equal to the difference in the V's over the difference in the U's. Put in your 0.6 for E. We don't know V2 or V1. We know that U2 is 3 minus U1 is 6. And then when you rearrange it, you get V2 minus V1 is equal to 1.8. You have two equations there, gents. So you would solve the simultaneous equations. When you solve them for V2, you get 6.2. Solve it for V1, you get 4.4. And what I do is I fill that into my table. And the reason I do that is because it's much easier than to manage the impulse and the kinetic energy, because all of the data is in a confined, neat space for you. You're not searching for anything. So the impulse. We're looking for the impulse acting on A and the impulse acting on B. So remember, the impulse formula is the difference in the momenta. The impulse in A will mean we're looking at everything in the A row, so the 6, the 4 and the 4.4. So we'll have 4 by 4.4 minus 4 by 6 gives me minus 6.4 kilogram meters per second. Impulse on B then, you're looking at the second horizontal line. And like the sentence says, they should be equal and opposite, and that confirms Newton's third law. Now the kinetic energy as well is easily to manage with the table. So the kinetic energy before is a half m1u1 squared plus a half m2u2 squared. That gives me 81 joules. And then the kinetic energy afterwards, a half m1v1 squared plus a half m2v2 squared. Gives me 77.16, and when you subtract the two, you get the loss in kinetic energy. Now it's time for you guys to do a question.